Okay, so those of you who are already seated, please scan this QR code and attempt a few quick quiz questions. Okay, so all good with this QR code? I'll give you 3 more seconds. 3, 2, 1, time's up. Okay. So, okay, good morning. It's week 3 and early 9 a.m. Monday of week 3. So, thank you for making it here. So the plan for today is trying to wrap up on what we've sort of left over last week. Okay, I'll just quickly go through those slides. What was left on last Friday, there wasn't anything that is really technical. Okay, and most of them are quite straightforward. So I'll just briefly go through them, and then we'll jump into model selection for higher order AR models. And before we start, let's look at the Padlet questions. So the first one is supposed to be very straightforward, basically testing whether you understand the definition of mean reversion. So here it says mean reversion in a time series implies that the series will continue to diverge from its mean over time. So is this correct or it's false? Obviously, it's a false statement. Okay, mean reversion means that the series will tend to revert back to its mean, not diverge. Okay, if it were indeed a divergence, that would be mean divergence rather than mean reversion. Okay, so the first one, it's a false statement. Now, the second one, it's closely related to mean reversion. So here it says a stationary time series with stronger persistence necessarily lacks mean reversion. So do you think this is correct or wrong? Okay, so this is a tricky one. It sort of doesn't really have any correct component, I would say. So remember, a stationary time series must have a constant mean. Okay? For a series to have a constant mean, it must revert back to its mean quite often. Okay? So a stationary time series always have mean reversion. It's just that the degree of persistence would affect the speed of mean reversion. So a stronger persistence basically means that the past has stronger influence on the future, so it will have a slower rate of mean reversion. But it doesn't mean it will not be mean reverting. So this is a false statement, okay? Stationary time series always have mean reversion. Persistence only relate to the speed of mean reversion, okay? And this is also related to what we discussed in, I think that was lecture 3, okay? So what we said is that the closer the alpha 1 is to 1, the slower the YT adjusts back to its long-run mean, okay? A stationary time series always have an alpha 1 that is less than 1 in absolute value theoretically, okay? So regardless of how large alpha 1 gets, it's still, as long as it still remains stationary, it must be mean reverting. So this is incorrect. Now, the last one, it's closely related to the last Padlet quiz we did on Friday. So there we had an AR1 model. And what we said is that in the end, if you remember what we did on last Friday, okay, so the last quiz question was that an AR1 model implies that YT is correlated with its immediate lag, YT minus 1, and uncorrelated with any future lags. And we say that this is a false statement, okay? Obviously, an AR1 does not rule out indirect correlation. Now, here, we're looking at an MA1 model. Remember, MA1 model is one where we rest Y on the past shock and the current shock. So Y is not modeled as its own past, but instead modeled as a function of the shocks. So while I'm not discussing the MA model during the lectures, you're asked to read the lecture notes yourself. And basically, it's just the same way of analysis applied to a different method, applied to a different model compared to an AR1, okay? So if we write out the model equation explicitly, basically this is the MA1 model. So do you think in an MA1 model, the autocorrelation is presented only at the first lag with no autocorrelation at any higher order lags? So if you have attempted homework 1, you would have known, or at least if you have read the lecture notes, you will have known that this is a correct statement, okay? MA1 is different from an AR1. And the most immediate difference is that for an MA model of order Q, there is no autocorrelation beyond Q lags. Whereas for an AR model of order P, there can be autocorrelation beyond P lags, okay? So if we look at this model, we can just write out the model equation for T minus 1, okay? So YT depends on the shocks at time T minus 1 and at time T. So for YT minus 1, this would depend on the past shock relative to T minus 1, which is UT minus 2, and also the current shock that corresponds to the period T minus 1. And remember, the error term UT follows an IID white noise, or just simply white noise. A white noise process has no correlation, okay? So basically, UT minus 1 is uncorrelated with UT, and UT minus 2 is uncorrelated with UT minus 1 or UT. No cross-correlation, only variances, okay? So what I'm saying is UT minus 1, okay, that is only related to the UT minus 1 in YT's equation, but it's not correlated with the UT, okay? These two are uncorrelated. Sorry, uncorrelated, okay? And similarly, UT minus 2 is uncorrelated with UT or UT minus 1. then what implies is that if we compute the covariance between yt and yt minus 1, we have the covariance between the mu plus theta 1 ut minus 1 plus ut with that mu plus theta 1 ut minus 2 plus ut minus 1, which is the equation for yt minus 1. Now, mu is a constant, doesn't matter for the covariance because it's not random. Ut minus 1 uncorrelated with ut minus 2 uncorrelated with either the ut minus 1 or the ut in the equation for yt. So first of all, we can get rid of the second lag, okay? What remains is we don't have ut being correlated with any of the lag error terms. So what is left is just the theta 1 ut minus 1 and the covariance between it with itself. So we have the covariance between theta 1 ut minus 1 with the ut minus 1, which, first of all, we can take the theta 1 out. That gives us the covariance between ut minus 1 and itself, which is essentially the variance. Okay? And given that we assume a positive variance as long as theta 1 is different from 0, which means we indeed have an MA1 model, okay? Because we have an MA1 given that the path shock enters the equation for yt. This is positive. So there is autocorrelation at lag 1. But imagine if we now consider that for lag 2. So we have the same equation for yt. Now, the second lag of y would depend on the second lag of the error term and also the third lag. And apparently you can see that there's no overlap in any of the shocks. Okay? Essentially, covariance is just 0 because they're all serially uncorrelated. Okay? So no overlaps. The covariance is just 0. And this would apply for any autocovariance that's of order higher than 2. Okay? So in an MA1 model, autocorrelation is presented only at the first lag, and there's no autocorrelation at any higher order lags. So this is a correct statement. Okay? So this is the key difference between an MA1 and the AR1. AR1 can have autocovariance at lag 2, lag 3, lag 4, or even more than that. Okay? This is apparent in the ACF plot on the slide. Okay? So this is just quickly checking up what has been covered in the last 2 weeks and also what you were required to read after the lecture. Now, coming back to last Friday, so we talked about the empirical illustration of an AR1 model, and we attempt to fit that to the GDP data and also the GDP growth. And first of all, we've seen that an AR1 fitted to the GDP data appears to be quite a good fit. Okay, so we sort of have that the random walk model seems quite consistent with the underlying pattern. Okay, we're trying to describe the pattern. We're not trying to explain the pattern. So there's no causality here, merely descriptive. So this is what we've covered on Friday. And we also get to hear about hypothesis testing in an AR1 model. And remember, whenever you're testing the hypothesis for the value of B, that is between -1 and 1, we always have the standard normal critical values, okay? Whereas if we're testing whether alpha being 1, that entails testing whether we have a non-stationary AI1. For that test, we have the same t-statistic, but we need to compare the t-statistic with a different distribution, okay? It's still the same setup of the hypothesis test, but our conclusion as to whether we should reject the null hypothesis of non-stationarity depends on a different distribution, which we'll see in chapter 13. So this is where we stop on Friday. Now, for the growth data, basically it's just the difference between the GDP. So it's the next period's GDP minus the previous period, and that gives us the growth. And we can see that for the fitted model, we have an estimated intercept of 1.995. Okay, this can be seen from the R results. And we also have the autoregressive coefficient. So the coefficient on the immediate lag being 0.338. Remember in a diagram, in a figure, we have that the GDP series sort of have an upward trend, whereas the growth data appears stationary, okay? And what we have here, the estimated alpha hat 1 being substantially less than 1 is further sort of supporting our visual guess of stationarity in the growth data series, okay? So that means the growth data is likely to be stationary. And also we could do hypothesis testing similar as in the GDP case for testing whether alpha 1 is equal to 0, and basically the t-value reported is the t-statistic for that test, 5.11, which is greater than 1.96, the standard critical values. So it's statistically significant, and we can also use it to test some other hypotheses. Now, what is more interesting about a stationary time series, okay, is that we can now estimate its long-run mean, and we can also estimate its autocorrelation function. So remember, for a stationary time series, a stationary AR1, the long-run mean is the ratio of intercept, the alpha naught, over 1 minus the alpha 1, okay? So the long-run mean is an unknown parameter because it depends on the unknown alpha naught and alpha 1, but we can estimate it using the regression result, okay? We have the alpha hat naught, which is 1.995. We also have the alpha hat 1, which is 0.338. Therefore, we can estimate the long-run mean using the sample data, and that gives us roughly 3.014. So the long-run mean, the estimated long-run mean of the growth series is roughly 3%. And we can also estimate the ACF, okay? So on Friday, we've sort of discussed that the ACF for a stationary AR1 at lag h is just equal to the slope coefficient alpha 1 taken to the power h. Okay, then again, for any pre-specified lag, okay, let's say h being 2, so we can estimate the ACF using the data. So the sample ACF at lag 2 is basically alpha hat 1 taken to the power 2. And using the regression result, that gives us roughly 0.114. And we can see that for an AI1 here, even though the alpha 1 hat is quite small, we still have autocovariance at lag 2. Okay? This is again different from an MA1, where typically there will be no autocovariance at lag 2. Okay? And we can see that this is different from 0. So remember, AR1 can always have autocovariance beyond the order of the AR model. So this is the regression result. Now, if we try to plot the actual data against the fitted value, so the blue line represents the actual growth series that we've seen previously, And the red dashed line basically represents the fitted AR1 model. So the values computed by plugging in the value of alpha hat naught and alpha hat 1. Now, we can see that compared to the GDP data, which sort of match the underlying data pattern quite well, here the AR1 doesn't really match the underlying pattern in the growth data well enough. We can see that it sort of captures the average level, okay? But, so the mean is roughly here, and it's consistent with what we sort of estimated, roughly 3, okay? But it fails to capture the volatility of the growth data. So it's sort of smoothing out the variation. It's too smooth. So basically, the AR1 model does a great job here in capturing the long-run mean, but it fails to explain the variation. So in order to better describe the underlying pattern, to build a better model for forecasting, okay, we need to consider improving our model. So either by including more lags, so we consider not just an AR1, maybe an AR2, AR3, AR4, or we can consider also introducing variables from other series. Like, for example, the interest rate, the unemployment rate. We know that from our macroeconomic theory, these are all related to GDP growth. And to some extent, we will expect that they will help us to explain the variation in the growth data. So we'll first discuss higher order AR model, and then modeling multiple series in the same regression. We'll come back to this in chapter 14, which is the last chapter of the time series analysis. So as long as we have analysis of a single time series under control, then analyzing multiple time series is sort of just extending what we've seen in the single series case. So coming back to the AR1 model, so here we can see that the AR1 model may not fully capture the rich dynamics of the underlying series, and this is because of the assumption it imposed. Okay, so remember, I think that was last week, we say that the conditional expectation of YT, given its own history, depends solely on the immediate past, okay? So this is basically coming from the assumption that the error term follows an IID white noise with mean zero variance sigma square u, and that it's independent of all paths. So this AR1 model construction gives us the conditional expectation being dependent only on the immediate path, yt minus 1. And second, okay, the conditional expectation is linear. So here we have two assumptions within the AR1 context. Then, in order to improve our model, first of all, is to relax the first assumption by introducing more lags. Okay? Then, in this case, we will allow the conditional expectation of YT to depend on additional past observations. Now, if we were to relax the second assumption, which is considering nonlinear models, for example, we introduce the YT minus 1 square. This is possible, but we're not going to discuss this in our course because it basically imposes some analytical challenges. So first of all, the condition for stationarity in this situation is very complicated. And we typically, in empirical practice, usually adding more lags often sort of like better captures the underlying dynamics compared to introducing linearity. And in topic 1, we sort of discussed that a linear model basically provides a linear approximation or the best linear approximation to nonlinear functions, okay? So a linear model is always a good starting point. Now, so what we're going to do now is we'll consider relaxing the first assumption. So consider an ARP model. So basically, we just add more lags into the model equation up to the p lag. The p can be 2, can be 3, can be 12, can be 24, depending on the context of your analysis. So in this case, it allows the direct influence of further passed on y compared to an AR1 model. Okay? So we can see that in this setup, we'll have the conditional expectation to be dependent on the first p lags. Remember, the conditional expectation of the error term, given all past history of y, is just 0, because the error term is assumed independence of all past history. Given independence, the conditional expectation must be 0. So for an ARP model, the actual statistical analysis is quite complicated, and we are not going to cover that in our course. But the main thing that you will have to remember is that the stationarity condition for an ARP, this is very crucial. Okay? And this is somehow similar to the stationary condition that we impose for an AR1. So remember, AR1, we required a slope coefficient to be less in absolute value. Whereas here, it's just that we require the sum of all the slope coefficients to have an absolute value being less than 1. So it's just we extend the condition in the AR1 case. So previously, we only had that one sec. So previously in the AR1 case, we have yt equal to alpha naught plus alpha 1, yt minus 1 plus ut. So the stationarity would imply alpha 1 to be less than 1 in absolute value. Okay? So what then for an higher order AR model, for example, an AR3, where we have yt depends on the first 3 lags. So we have yt minus 1, yt minus 2, and also yt minus 3 entering on the right-hand side. Then stationarity would depend on all 3 slope coefficients. Okay, so for stationary, we require alpha 1 plus alpha 2 plus alpha 3 to have a sum that is smaller than 1. Then extending to the general case, an ARP model, we require the sum of alpha 1, alpha 2, alpha 3, all the way to alpha p to be less than 1 in absolute value. So this is the key condition for stationarity. And this is something you should really remember. So this is the condition for stationarity. So if we inspect the time plots and also the ACF plot, basically it will be very similar to the AR1 case, although with a bit more complicated patterns, but still it will have a geometrically decaying ACF, just like what we've seen in here, okay? For ARP, we'll still have the ACF having this pattern, decaying geometrically, and we'll also have the mean reversion pattern, okay? Given that it's stationary, it will always fluctuate around the constant mean. So the visual characteristic of higher order AR model are just very similar to the simple AR1 case. Now, oops. One final thing on the ARP characteristic is that in this situation, the autocorrelations are more direct, okay, compared to an AR1. So, for example, if we look at the AR1 model, so YT is directly correlated with YT minus 1. and it's yt minus 1 that it's directly correlated with yt minus 2 through the AR1 equation for t minus 1. So in a sense, yt minus 2 is correlated with yt through the yt minus 1. Okay, so this is an indirect correlation. Between the yt minus 1 and the yt minus 2 and yt. Okay? Now, imagine if we now have an AR2 model. So we have yt being not just a function of t minus 1, but also a function of t minus 2. So first of all, yt minus 2 will now directly influence yt. Okay, so there is a direct correlation here. And at the same time, it will still influence yt through the yt minus 1. Okay, so yt minus 1 is a function of yt minus 2 and yt minus 3. So we can see here, it also influences yt indirectly through yt minus 1. So a higher order AR model not only allows indirect correlation, but it also allows direct correlation at higher order lags. Okay? So this is why the ARP model allows us to capture richer dynamic of the underlying time series. So this is the ARP model. Now, coming back to our growth data example, previously we've seen that the AR1, while capturing the mean quite well, it fails to capture the volatility. Now, suppose we fit an AR2 model to the growth data, basically just by incorporating an extra lag. So basically, we can see here the 1 stands for the coefficient attached to the first lag, and the 2 stands for the coefficient attached to the second lag. Okay, which is why the alpha hat 1 in an AR2 model is the 0.277, and the alpha hat 2 in an AR2 model is the roughly 0.179. Okay, and we could see that both lags are individually significant at 5%, because for the first lag, the t-value is 3.9. Okay, for the second lag, the t-value is 2.5. And basically, the statistically significant second lag further supports that this AR2 model is actually useful in describing the underlying pattern. Okay, so incorporating the second lag is statistically justified. Now, we can also see that if we try to sum the estimated coefficients, the two slopes, they will give the sum is roughly 0.45. Okay, that is still well below 1, but it confirms the stationarity of the underlying time series. Okay, so basically that suggests the past observation has diminishing influence as time passes. Now, if we plot the data, okay, so this might look a little bit messy. So again, the blue stands for the actual series, the red comes from the fitted AR1 model that we've previously seen, and the green one is the fitted AR2 model. Okay. So first of all, from the last slide, we've seen that the second lag is statistically significant, which does indicate that adding this extra lag is helpful in explaining the variation in Y. However, we can still see that for an AR2, it still fails to capture much of the volatility. Then this sort of leads us to a very important question. How many lags are enough to model the underlying dynamic accurately? Okay, so this sort of relate to the question for determining the optimal lag order of an ARP model, which is what we're going to discuss today. Okay, so lecture slide 5. Okay, so this is the sort of the key concept that we're going to look at today. It's all about the bias variance trade-off and finding a method that sort of balances these two considerations. And we've seen this previously in topic 2 when it comes to model selection. Okay, when does it make sense to add more variables, and when does it make sense to consider, including interaction terms, blah, 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 additional, let's say, right-hand side variables into the model equation? When should we do that? What is the advantage for doing that? And why shouldn't we include too many variables? Okay, this is analogous to what we're discussing here. So the advantage of a larger P, which is the advantage of including more regressors or more explanatory variables on the right-hand side, that's basically improves the model flexibility, okay, in a sense that it allows us to capture the true dynamics of the underlying time series more accurately. And this would, in a sense, reduce the model bias if the underlying time series indeed depends on longer history compared to a shorter one. But it comes with some pitfalls, just like in cross-section case. Including too many variables on the right-hand side of the equation. So here, including too many lags, basically that will lead to a higher estimation variance. Given the fixed sample size, the more parameters you have to estimate, the greater the variation in the estimated coefficients. So there's greater estimation variance. The alpha hats will have a larger standard error. Okay. And another important consideration, especially related to forecasting, is that this would lead to a situation called overfitting. So essentially, it just means that the model equation fits the given data too well. Okay, so it not only So basically not only captures the underlying pattern in a sense, it also explaining the random fluctuations, okay? Also capturing the random fluctuation coming from the shocks within the given sample. But this would lead to a problem in generalizing the model to unseen data, okay? So basically, the overfitting is a problem of explaining the in-sample data but fails to explain the out-of-sample data, leads to a poor forecasting model. Imagine the shocks, okay? The shocks are random. The random shocks that happen within the given data might not be the same as those happening out of the sample, okay? So the model that does a good job in explaining the in-sample variation or too good a job might fail to explain the out-of-sample variation accurately. So in a sense, it's sacrificing the out-of-sample performance for a better in-sample fit, okay? So this is the disadvantage of having a large P. So essentially, the model selection method is about finding the balance. We know that beyond a certain point, adding more parameters would just sort of implies picking up noise, not the true underlying structure. And the goal here is basically to find a P that generalizes the model well, not only performs well in sample, but also performs well out of sample. So we'll be covering two model selection methods. One is called stepwise testing. So basically, we start with a large model, we gradually test downwards, okay, stepwise, so follow a step-by-step, reducing the model smaller and smaller. Another method that we'll be discussing is called information criteria. In a sense, the logic of the information criteria is quite similar to adjusted R squared, Okay, so it not only takes the model fit into account, but also takes the number of parameters into account, and it imposes a penalty on the number of parameters. The more parameters you include in the model equation, the heavier the penalty. So I don't think I'll have time to get to information criteria today, so I'll leave that for Friday. But I'm going to quickly go through the stepwise testing. It's very simple and straightforward. Basically, it's just sort of a set of t-tests. So essentially, we try to identify the optimal order P within a range. Okay? Remember, whenever you want to model something, okay, whenever you're considering an AR model, there is always an extent to which, or like a maximum limit, how many parameters or how many variables you should include on the right-hand side. Okay, and that the same applies for an AR model. So we'll typically set a limit as the highest or the largest P that we should be comparing or considering to some other values of P. This is what we denote as the Pmax. Okay, and basically the value of Pmax is typically informed by either the theory, okay, or by some initial analysis of the data. By theory in a sense that, imagine if we have a quarter data, okay, then we might consider using lags up to the 4th or the 8th. Okay, that sort of allows us to measure or regress the AR model in an annual basis. Or imagine if we have monthly data, then one might typically consider adding up to the 12th lag. Okay, so this is the Pmax, basically the maximum order of the AR model that we would consider comparing or testing or selecting against. And this process basically means that we'll start from the highest possible order. Okay? We start from Pmax. Suppose Pmax is 6. We start from an AR6. Then we start from estimating the AR6 model. And what we're going to do is we'll perform a hypothesis test on the slope coefficient for the 6th lag. Okay? So we're testing whether alpha 6 is equal to 0 using the standard normal critical values. If we fail to reject the null, which means that the last slope coefficient, the alpha 6, is not statistically significant, then we will reduce the P by 1. Okay, so 6 minus 1 becomes 5. We go back to step 1, which means for P being 5, we will re-estimate the AR5 model. And then we'll continue a new test. We estimate the AR5 model, and then we do the t-test on the highest order lag of the AR5 model, which is the alpha 5. Okay, we'll consider, and then we'll continue this process until we reach the first rejection. If the null is rejected, then we'll identify the current value of P as the optimal one. So for example, if we fail to reject alpha 5 being 0 in the AR5 model, then we stop the test and we conclude that P being 5 is the optimal. So the first significant lag being 5 basically means that the higher order lags are all not significant. Okay? So if the alpha 5 is statistically significant in an AR5, that basically implies YT does not depend on the 6th lag, the 7th, the 8th, or even higher order lags. Okay? This is the intuition. On the next slide, we'll see an example. So before we look at the example, so there are some important considerations for using this method. So there is a risk of spurious significance. And in fact, this is a risk that will appear to any hypothesis testing. Remember, there's always a chance that we are committing an error. Let it be a type 1 error or type 2 error. Okay? So in the stepwise testing, some higher order lags may appear significant purely by chance. Okay? So that would lead to potentially misleading conclusion, okay? And also, there is a chance that we are overlooking more simple models because we stop at the first significant lag. Let it be 5, okay? It could be that actually an AR3 model is a better fit compared to an AR5, but the stepwise testing does not allow us to consider the AR3 because it tells us to stop at the AR5, the first significant lag, okay? So in a sense, this selection method sort of kind of reduces the possibility for us to look for a simpler model that might imply a better fit. So before I let you go, as an example, using the growth data. So here, I started with supposing the Pmax being 4 because the growth data is measured on quarterly basis. So we can see that we start with an AR4, and we would need to test the highest order lag, which is the 4th one, alpha 4 being 0. We can see from the result that this t-value is very small, 0.9, which is far below 1.96. So we will fail to reject the null hypothesis. That means we should reduce the order by 1 and proceed to an AR3 model and estimate that. So once we have estimated the AR3 model, what we want to do is to test the highest order lag in the AR3, which is the alpha 3, the last row. And here we have a t-statistic that is minus 0.119. Okay? The absolute value is less than 1.96, again, suggesting that we'll fail to reject the null. So we'll proceed to the AR2 model. Now, in the AR2 model, which is what we've seen previously, we have a t-statistic that is 2.57 greater than 1.96. So that implies we should reject the null here, we should stop the stepwise testing, and we should conclude that AR2 is the optimal order for the growth data. So that's it for the stepwise testing, and I will come back to the information criteria on Friday. One last thing before I let you go. So we have quiz 1. The pre-work instruction is already uploaded on Blackboard. You can find it under the semester 2 assessment. Okay, so that's a new assessment page for semester 2, just to make everything stay organized. And the past session starts this week. If you're interested in that, you should check out the semester 2 timetable. I have also set a time for the midterm exam. Okay, so basically, duration is still 45 minutes, but because the scheduling of the lecture is at 9 on both Monday and Friday, I sense that starting the quiz at 9 is not a good approach. So what I'm going to do is I'll give you a 3-hour window from 9 to 12. Okay, basically you have the 3-hour window. You have to complete the midterm exam within 45 minutes in the given window. Okay, and I'll give you more details as it gets closer to the midterm. So that's the sort of the structure. Okay, thanks for coming. I'll see you on Friday. Remember, on Wednesday, the quiz 1 window will open, and I think I'll give you a brief report or an overview of the final exam for semester 1 on Friday. By then, I should have a report ready. Okay, thank you.